When you build your virtual machine, you have a number of options relative to the hardware complement of that VM. And those options are dependent on the version of ESXi that you're using. The later or the more current your version of ESXi, the more options that you have when you're building your virtual hardware. Now, what you see here in this slide represents hardware version 17, which is current as of vSphere 7 or ESXi version 7. Okay, so let's take a look at the capabilities of ESXi version 7. If you're interested in running an older version of ESXi, or you've got multiple versions of ESXi in your environment, you might want to choose an older hardware version, which may not have the same set of features that we're going to describe right here. So, with hardware version 17 for ESXi 7.0, you can have virtual machines with up to 256 virtual CPUs. Of course, that is going to correspond with the number of logical CPUs that you have on your host. You can't have more virtual CPUs than you actually have cores on an ESXi host. Also consider that hyperthreading is in there as well. So if you have hyperthreading, you can double that. You can have virtual machines with up to 6 terabytes of RAM. Virtual machines can support hardware 3D if you have the physical hardware that exists in your ESXi host from AMD or NVIDIA. You can have up to 10 virtual NICs. You can have an IDE controller with up to 4 IDE devices on there. Typically, those are used for CD-ROM devices and that sort of thing. You can have up to 3 parallel ports and 32 serial ports on your device. We have an AHCI serial ATA controller that actually supports up to 30 devices per adapter there, for a total of 120 serial ATA devices. Now, typically those are also used for more modern operating systems when we're attaching SATA-based CD-ROM drives. You can have a USB controller with up to 20 USB devices attached to your virtual machine. Literally a floppy drive with up to a floppy controller with up to 2 floppy drives attached. We attach those similarly to an ISO image would be to a CD-ROM drive. We have a .FLP image that you can attach to a virtual floppy drive. Now here's where it starts getting really interesting in terms of your hardware complement. If you have NVMe devices in your ESXi hosts, you can build a virtual NVMe controller, up to 4 of those controllers for each virtual machine, with up to 15 NVMe devices on each of those controllers. Now, most of the time, our virtual disks are attached to virtual SCSI controllers. Okay? We can have 4 virtual SCSI controllers. By default, each of those SCSI controllers can have up to 15 SCSI virtual disks attached. But if we use a special VMware proprietary paravirtual SCSI adapter, we can have up to 64 virtual disks on each of those 4 SCSI controllers. Each of those virtual disks can be up to 62 terabytes in size. Finally, of course, we've got our mouse and our keyboard. So I mentioned before that the virtual motherboard that you saw on the previous slide was based on the capabilities of vSphere 7. And in fact, with each release of ESXi, our virtual motherboard capabilities continue to grow and expand. So if you'd like to use older versions of ESXi in your environment, you might choose to build a virtual machine on an older version of the virtual hardware. You see here a table of hardware versions that correspond with ESXi versions. Note that hardware versions 12 and 16 were specific to VMware Workstation and Fusion Pro. Okay? So they didn't just drop off the radar there. But suffice it to say, if you would like a virtual machine to run on a version of ESXi that is older than version 7.0, the virtual hardware must not exceed the capabilities of the ESXi that you're running it upon. Also note that you really can't roll back. I can't take a virtual machine and downgrade it to a previous version, but I can take a virtual machine if I power it off and upgrade it to the latest version that is supported on the ESXi host to which that virtual machine is registered. Now, when it comes to CPU and memory, right, there are a number of things that we can do here. Okay? We can reconfigure that virtual CPU, we can reconfigure that virtual memory, and we can do that if whether the virtual machine is powered on or powered off, depending on the capabilities of the guest operating system that we have installed. Now, there are some maximums that might be smaller than the maximums that we have for ESXi in general. If you'll remember, we can have up to 256 virtual CPUs, but you have to have the corresponding physical hardware to match that. So if you only have, for example, 22 hyper-threaded cores in your ESXi host, then ESXi will prevent you from creating or running virtual machines that exceed 44 virtual CPUs. Now, does that mean I should be building virtual machines with 44 virtual CPUs on a host with only 22 physical cores? Well, probably not. Hyperthreading itself doesn't necessarily double performance. So we should consider really when we're planning this sort of architecture that we shouldn't exceed the number of physical cores on any particular single virtual machine. When it comes to memory, things are a little bit different, but we also have to consider that for every page of memory that we request or that is requested by a virtual machine, there has to be a physical page of memory that will correspond with it. The maximum memory size for a VM will then depend on the maximum amount of RAM you have on your ESXi host, as well as the hardware compatibility level that you have set for your VM. For ESXi version 7, that number is 6 terabytes, at least with the initial release of vSphere 7. Now, when it comes to virtual storage, each of your virtual machines have to have a storage controller. Okay? We've already mentioned serial ATA, right, for AHCI. We also have an IDE controller, but by default, each of your virtual machines will also get a SCSI controller. And that SCSI controller that is chosen will be based upon the guest operating system that you choose when you build the virtual machine. ESXi knows if your operating system has a built-in driver for these first 3 specific types of virtual storage controllers: Bus Logic Parallel, LSI Logic Parallel, or LSI Logic SAS. In modern operating systems, LSI Logic SAS will likely be the choice for you. But if you're using older operating systems, it might choose the LSI Logic Parallel if that driver happens to be built into that operating system, or a Bus Logic Parallel device for stuff that's even older. Things like Windows XP get a Bus Logic Parallel SCSI controller. Now, if you have virtual machines that you know are going to drive a huge amount of storage traffic, we measure this in IOPS, or I/O operations per second. Okay? If we exceed or expect to exceed 2,000 operations per second, then we might choose VMware's Paravirtual SCSI adapter. And that will improve performance as your virtual machine is accessing SCSI storage. Okay? Now, we already mentioned AHCI serial ATA controllers that we will typically attach a virtual CD to, but we also have virtual NVMe controllers if we have the corresponding hardware to attach to. Now, when we build our virtual disks that attach to those storage controllers, we have a number of options. Okay? And we describe the layout of those virtual disks based on the type of provisioning we build for that virtual disks. And there's a couple of options that we have. The first one is called a FIC provisioned virtual disk. What a thick provision virtual disk will do is it will have all of its blocks pre-allocated, set aside by ESXi on your storage, so that if I build a 100 gig thick provisioned virtual disk, then a 100 gigabyte VMDK file will be created on the storage device that you've chosen, on the data store. Okay? Now there are two types of thick provision disks that we can have within vSphere. And the first one is an eager zeroed thick provision disk. Think about this like a hard drive that is fully formatted. Okay? What we'll do is we'll create a virtual disk, create the start partition, create the end partition, and fill the entire virtual disk with zeros. Anytime we want to write to a block of storage, that block of storage has to be written first, at least once, with zeros before we can actually write our data to it. So when you create an eager zero disk, we pre-write all of those zeros. In theory, we may have faster write performance when we're building an eager zero disk versus a lazy zero disk, where we do not write the zeros ahead of time. In a lazy zero disk, we simply write the entry of the partition table, we write the end of the partition table, and we call it done. Lazy zero disks are very, very fast to create. Write two little table entries and we're done. But an eager zero disk, we have to write all those zeros out. Think of a lazy zero disk as a quick formatted disk. Now, anytime we want to write data to that lazy zero disk, every block needs to have a zero there. So if we don't have any data on that block, we'll write the zero and then we'll write the data. That can take a little bit of time, but in modern storage arrays, that time is so fast that most of the time we won't notice any performance difference at all between a lazy zero disk and an eager zero disk. Suffice it to say, the nice thing about a thick provision disk is we can go to a storage array, say that we've got a 100 gig disk, and we know that we have 100 gigs of disk space that has been allocated to our virtual disk, and we won't have to compete with other virtual disks in that space like we might with a thin provisioned virtual disk. Now, in a thin provisioned virtual disk, we do not pre-allocate the blocks. A 100 gigabyte thin provision disk will start out with a very small disk descriptor and 64 kilobytes of data. And then as we begin to write to that thin provision disk, that VMDK file itself will begin to inflate and consume disk space with the data that we've now written. So what are the advantages and disadvantages to these different types of storage? Well, the advantage to a thin provision disk is that if somebody tells me I need a 100 gig disk, I'm not really sure if they actually need the full 100 gigs. And if they never write 100 gigs of data, say they only write 20 gigs of data, then that virtual disk will never consume that full 100 gigs. It'll only consume 20 gigs. So that makes my storage much more efficient in terms of capacity. And when we're dealing with enterprise class storage array, this capacity can be very expensive. When I build a thick provision disk, if somebody tells me I want a 100 gig disk, they get their full 100 gigs. We have a 100 gig file. But if they never write more than 20 gigs of disk, that's 80 gigs of disk space that I'll never get back. Okay, so that's all well and good. We understand the differences there. What are the drawbacks then to a thin provision disk? Well, I asked the question like this. How many 100 gigabyte thick provision disks can I put on a 1 terabyte storage array? The answer is obviously 10, right? 10 100 gig disks time, is 1 terabyte of disk space. But how many 100 gig thin provision disks can I place on a 1 terabyte data store? Well, the answer to that is a little bit more complicated. Like I said before, we only consume 64 kilobytes of disk space when we build our initial thin provision disk. So now I can take 1 terabyte, divide that by 64 kilobytes, and the number is massive. All right, so I'm potentially putting thousands of 100 gigabyte thin provision disks on a 1 terabyte storage array. What's the drawback? Well, I only have 1 terabyte of actual disk space to work with. Now I start powering on these virtual machines. I start installing operating systems. I start writing data. And pretty soon, each of those virtual machines, though they believe they have a 100 gigabyte hard drive, there's not necessarily 100 gigs of disk space for every single one of those virtual disks. And my storage array might run out of disk space. And as soon as that happens, every single virtual disk and the operating systems and guest OSs that have them attached and the software that's running in those might fail. And in fact, in all likelihood, it would fail. So what can I do? Well, if I were a good vSphere administrator, I would actually begin to monitor the physical capacity available on my storage array. I would use thin provision disks, but make sure that I have enough capacity available on my storage array so that I haven't so overcommitted it that I might actually run out of disk space. So that's my job as a vSphere administrator. Now, VMware's job to help the vSphere administrator is to set alarms and alerts within vCenter to notify us when I might be running out of disk space. And we'll begin those notifications at 70 and 80%, or I think it's at 80% of full capacity on my data store. So I can tell you that in today's world, most of our virtual disks actually are thin provisioned, and it's up to the vSphere administrator to make sure that there's plenty of disk space available to support more thin provision disks than would be capable of being supported by a storage array if those thin provision disks were fully utilized. Okay? That's quite a mouthful, but the long and the short of it is keep an eye on the total physical capacity available on your data store. Now, there is some differences in the performance and in the creation time of these virtual disks. So this chart kind of lays out some of those differences. Let's have a look. For thick provisioned lazy zero disks, the creation time is very fast. We do pre-allocate all of the blocks. And in terms of the layout of those disks, there's a pretty high chance that those blocks will be contiguous, right? All those blocks will be laid out right next to each other. Now, in modern storage arrays that are spinning disks, we're using a RAID sort of configuration anyway, and contiguous blocks are not really necessarily that important to me. If we're using SSDs, we never have contiguous blocks. We're just writing all over the place, and it doesn't really matter. Okay? When it comes to zeroing out the blocks on a thick, lazy zero disk, the blocks are zeroed out upon first write. Now, when it comes to a thick, eager zero disk, the creation time of that disk is actually pretty slow. We have to zero out all of those blocks. Think full format. How long does it take to format a full, what if it was really large, 20 terabyte virtual disk? It can take quite a bit of time. We will pre-allocate those blocks. We have a very high chance of contiguous file blocks if we're using spinning disks. And we zero out those blocks right at the beginning. So we might have a chance of seeing a little bit better write performance. Now, when we thin provision a disk, the creation time is absolutely the fastest. Okay? We only allocate the disk space when we try to write the disk. Okay? So it's done at first write on demand. Okay? Now the layout is going to kind of be all over the place because you might have one virtual machine over here, one virtual disk here, another virtual disk here, and then this guy tries to write, so it's going to write over here and so on, right? So we're going to have kind of stuff all over our storage array, but a modern storage array can handle those sorts of things, and we don't have to worry about things like fragmentation of our storage arrays very often anymore. It's kind of, well, it really, those concepts, especially when it comes to solid state drives, are in the past for us, and we don't have to worry about it as much. Okay. Finally, blocks do need to be zeroed, and they are zeroed on first write. Okay, so that gives you an idea as to thin versus thick provision disks. Now, when it comes to virtual networks, like virtual SCSI controllers, it's important that we make the right choices for our virtual machine. Most of the time, 99.9999 whatever percent of the time, when we build a virtual machine, it's got to be attached to a network somewhere, which means that virtual machine needs a virtual network adapter. Now, just like there are multiple types of SCSI controllers, there are also multiple types of virtual network adapters that we can attach to our virtual disks. Not only do you have to choose the right type of network adapter, but you also need to choose the virtual network to attach that virtual network adapter to. And in Module 5, we'll get deeper into describing the different types of virtual networks, okay, and virtual machine port groups, which is how we attach virtual machines to those virtual networks that are eventually attached then to or passed through to the physical cards on the ESXi hosts and then out to the rest of the network. We want to know whether or not that virtual NIC is actually connected, okay, and whether or not to connect that virtual NIC when the VM powers on. Usually the answer is yes. Now, like I said before, there are a number of types of virtual network adapters that are available to us. When ESXi builds a virtual machine and you've chosen the guest OS type that you are going to be installing, ESXi will tell you the most appropriate virtual network adapter. The most appropriate virtual network adapter is not always the one that you should use. What makes it appropriate is that that guest OS, in all likelihood, has a built-in device driver for that virtual network card. For the most part, the default is going to be an emulation of an Intel E1000 or E1000E network adapter. Now, those are gigabit network adapters, and if you leave it on that default, your virtual machines will only participate on the network at gigabit speed, regardless of if you have physically higher speed network adapters on your hosts. 10 or 25 or 40 or 100 gig adapters or more, right? Your virtual machine will only participate at 10 gig speed. So instead, what you might want to choose is VMware's paravirtualized VMXNet3 adapter. Now, there are a huge number of advantages to the VMXNet3 network adapter. So I will go out on a limb and I will say you should always use the VMXNet3 adapter. I'm going to show you a couple of exceptions to that a little bit further down the road in these slides. But by default, you should switch from the E1000 to a VMXNet3 network adapter. Now, this is a proprietary network adapter meant to work in the VMware ESXi environment, and it works really, really well. But what are the chances your guest operating system will have that device driver in among its complement of devices that you can attach? Well, it's not very high. Believe it or not, some vendors of Linux are actually starting to include the VMXNet3 adapter in their distributions by default. But if you don't have the VMXNet3 adapter, you can always install it simply by installing VMware tools in your guest operating system. Now, the flexible adapter is an older adapter, and it's given by default to guest operating systems like Windows XP, who don't have an E1000 adapter installed by default. Now that flexible adapter actually emulates an AMD PCNet 32 adapter, which Windows XP actually does have by default in its ISO image as you install Windows XP. So be aware of that. Another thing that you can do is dedicate a physical adapter to a particular virtual machine. And we call that PCI pass-through or direct path I/O. And when you do this, there are a couple of options. One of them is called single root I/O virtualization, which allows you to, with certain operating systems, dedicate that physical NIC on your host to a virtual machine. Another way to do it is by using vSphere's direct path I/O. What this allows us to do, like I said before, is to dedicate a physical network adapter to a particular single virtual machine. Actually, in vSphere, we now have shared direct path I/O devices as well. So you can actually support things like vMotion, for example, with direct path I/O. But the idea here is, in your virtual machine, you would need to install the device driver for that physical adapter. Finally, we have here a paravirtualized RDMA adapter, which allows a virtual machine to use remote DMA type Ethernet adapters. Now, there's a whole slew of other virtual devices that we can attach to our virtual machines. CD and DVD drives, which we would attach ISO images to. We support USB 3.0 and in vSphere 7 3.1 host controllers, so you can have USB 3.0 and 3.1 devices attached to your virtual machine. And those devices can be either attached to the system that your vSphere client is plugged into, like a laptop, for example, or it can be directly attached to an ESXi host. Finally, we'll have a look at the virtual machine console. Now, I mentioned before that in order to properly interact with a virtual machine console, especially if it's a graphical-based operating system, you really want to have VMware tools installed. Now, once you've got VMware tools installed, there are a number of options for you when it comes to which VMware console you'd like to use. In the vSphere client, we have a web-based VMware console, and you can see that you can launch it right here, Launch Web Console. This brings up a console for that virtual machine in a new browser tab, right? So that console's in a browser tab. It works pretty well, but honestly, we've got some better options as well. What you might want to do is install an external piece of software. There are a couple of remote console applications that you might choose from. You can go to VMware and you can download the VMRC application, which is actually a nice little Java-based application. And when you select Launch Remote Console, it launches this little application and gives you a very nice console. If you happen to have VMware Workstation installed or Fusion Pro, those can also act as an external remote console. So you click on Launch Remote Console, and Workstation will pop up and show you the console for that virtual machine. And from there, you can work with the virtual machine quite nicely. My recommendation would be to use these remote consoles only when other types of external access are not available. For example, if you have a Linux-based virtual machine, you might want to use SSH. If you have a Windows-based virtual machine, you might want to use Microsoft's remote desktop protocols and those sorts of things, because they tend to perform a little bit better than the consoles that you have here available from VMware. Okay? It's really up to you at that point. If you're doing just a little bit of interactivity, then the console's fine. Okay. Now, finally, we're going to jump into lab number 5. And lab number 5 has us actually launching the host client to have a look at the virtual hardware configuration. And we're going to do things like add some virtual hardware to a virtual machine. So we'll first examine the virtual machine's configuration. We'll add a virtual hard disk to the VM. We'll then compare some thick provision disks with some thin provision disks. Once that's complete, you've completed lesson number 2 here in module number 3. We've looked at the files that make up your virtual machine. We've looked at the different versions of VMware hardware, okay, those different versions of the virtual motherboard. We've looked at the different virtual components of each of a VM. We've looked at the vSphere client so that we understand what to look for as we're examining the virtual machine. We've got an example of how we might interact with that virtual machine through the console. We've looked at the different network and storage controllers, looking at VMXNet 3, looking at the Paravirtual SCSI adapter, and so on. And we know all there is to know now about thin provisioning versus thick provisioning. So I hope you've enjoyed that lesson. And when we come back, we'll have a look at containers. We'll see you real soon.